Hi again everyone, Chris Tisdell here. In this presentation I'm going to show you how to solve some basic partial differential equations via a change of variables. Now this video is one of a series about this subject, and in other videos I'll be doing some examples and discussing rotation of axes and other kind of change of coordinates. But this particular video is why does the general case work for non-constant coefficients in our PDE. So let me give you an idea of what I mean. This is the general linear PDE that we're going to discuss. So here A, B and C and D are potentially functions of x and y. U is the unknown function of x and y, and the subscripts denote partial derivatives. Okay, so how do we solve this using a change of coordinates? Well, with a change of coordinates, we want to take something that's complicated and reduce it to something that's simpler. Now we are going to introduce a new set of coordinates, psi and eta, and essentially what we're going to do is transform this PDE into a PDE where there's only one derivative present. So it's almost like an ODE, if you like. Okay, so that's the general aim with the change of variables and PDEs. Okay, so the question is, how do we actually determine what these change of variables should be? That's the big question. Okay, so I'm going to show you how to do that in this video. Alright, so let's think of U, a solution U to this problem, in terms of the psi and eta. And let's recast 2 in terms of partial derivatives involving eta, x, psi and y. Now if we use the chain rule, now just with the chain rule I tend to like to draw little pictures. Okay, so u sub x, go from letter to letter, form a derivative and go to an x. So u sub psi times psi sub x plus u sub eta times eta sub x. That's the first one. And then u sub y, just go along all the paths to a y. So these are your two expressions for u sub x and u sub y in terms of these other derivatives. Now, if we take these derivatives and substitute them into 2, then we get something that looks more complicated. But remember, our aim here is to simplify everything. Okay, and now what I'm going to do is choose either this to be 0, this coefficient to be 0, or this coefficient to be 0. Okay, so so if I want, let's work with this one and forget about that one. If I choose this, if I choose psi, so this happens, then that expression, well, that term will disappear, and lo and behold, I've got a PDE where only one partial derivative of the unknown function u is present. Alternatively, you could have this, and then that would disappear, and you'd still have only one partial derivative of the unknown function appearing. Okay, so the point is, these are simple PDEs that we know how to solve. Okay, so suppose we want to solve the first PDE. Okay, and we forget about that one. Let's solve this one so this coefficient disappears and we just get a differential equation involving u sub eta. Now how do we solve this? Well, we know that the solution to this partial differential equation is constant along curves that satisfy this differential equation here. Okay, So if we solve this differential equation, say, and we form some sort of implicit form of solution here, C would be a constant, what we can do is choose our psi to be this left-hand side. Okay? Now, I've talked about the solutions to these problems in other videos. Okay, so we know how to solve those from previous videos. Essentially what you do is you form this differential equation, you solve it along all those curves that satisfy this equation. The solution to this problem is constant, and in this context we're going to choose psi to be the left-hand side, I guess, in this context of the solution to dy dx equals b on a. Okay, so the important thing here is that psi is chosen in this way. Okay, so that gives us some insight on how to choose psi. What about the other variable, eta? Well, because we've concentrated on solving this equation here, this term will disappear. But we don't want this term to disappear. We want that to be non-zero. So let's choose eta so that this is simple, but it doesn't disappear. So if I choose eta as a function of one variable only, this will be 0, and one, say x, this will be 0, but this will just be a. Okay? So then we've simplified this enormously. This term will disappear, this will disappear, and we'll just get something like the following. So here, this is a PDE where only one derivative is present of the unknown function. Okay, so this can be solved by standard ODE techniques. Now, just as an aside, the change of coordinates here and here are known as non-degenerate, as the determinant of the Jacobian, which can be worked out as this determinant here, is non-zero. Well, why is this non-zero? Well, if this was 0, then psi sub x would also have to be 0 from this equation here. And then if you take the derivative of, say, this, okay, you get 0. All right, so what does that mean? It means that this b up here would have to be 0. But if b is 0, then in our original equation, we've only got one, this would disappear. We've only got one derivative anyway, so we wouldn't have to do anything. Okay? All right, that's just a smaller side. Okay, so we can now solve this problem using standard linear ODE techniques. Okay, so we've got our change of variables. If, on the other hand, we went through and worked with this equation, you could get eta from the solution to this differential equation, and then you could choose a psi just to be x again, and you would end up with a very similar equation where you just change the subscript essentially. Okay, so that's why the change of variables works, and essentially we're going from something complicated to something simple which we know how to solve. Now in other videos I'll do some examples showing you exactly how to choose the psi, for example, and the eta, but those will be the subjects of other presentations. I hope you can join me then.